morning, my chemistry students. Today is day 2 of periodic trends. We are looking at standard F, where we are using the periodic table to predict properties of the elements and their trends. There are some specific ones that we look at based on our standards. Today, we are actually going to be using the trends that we learned yesterday, but I do want to start by reviewing all the trends that we saw yesterday, in addition to just some stuff that we've seen so far relating to the periodic table and patterns this unit. Now, as we are going through this quick overview, I want y'all to realize that anytime I draw a right arrow, I am referring to going across a period. So from left to right, from group 1 through group 18. Anytime I draw a down arrow, I'm referring to going down a group. So the first trends we're going to look at are actually ones that you can read on the table. I like those because they're straightforward and simple, and they're kind of mistake proof as long as you look at your periodic table. So of course, my atomic number, the number of protons in the element as we go across, increases each and every time. And as we go down, has a significant increase in the number of protons in my nucleus. Not only do the number of protons increase each time, but so do my number of neutrons, and some of them increase significantly. So either or, those two trends are easy to see because they're actually on our table. The third one, nuclear charge, it's the charge of the nucleus. So we're thinking about the number of protons. And since it's related to my number of protons, it has the same pattern as my atomic number. So we increase down and increase across. Those three, I would say, are probably the easiest trends because they are on our table. The next set of trends that we're going to look at, I'm actually going to start by looking at metallic nature because it kind of ties into some of the others. So metallic nature, if we remember on our periodic table, we've got our metals on the left side of the table, and then we've got our little staircase with our metalloids on them. And then on the right side of that staircase, we've got our non-metals. So though this is not explicitly on our periodic table, if you can remember where they're located, you can infer the trend. So as I'm going across the periodic table, that's the easy one to see. I can see that I am getting less metallic. We're going from a metal to a not metal. So therefore, my metallic nature is decreasing. As I go down a group, it's a little bit harder to see in my transition metals, but we can see it fairly well in group 1 and definitely great in groups 13 through 17. So I'm going to pick on group 14 to be specific. I've got carbon, who's a non-metal, and then I've got silicon and germanium, who are my metalloids, tin, lead, and element 114, who are my metals. So we go from being not metals to metals, therefore we have an increase. Now, though this is not explicitly on our table, as long as we know the position of the elements, we can actually infer it. So yes, that means some metals are more metallic. They have a stronger metallic nature than other metals. Now, my metallic nature happens to have the same general pattern as my phases of matter. So our metals are on the left side of the table. That's where my solids primarily are found. SOLIDS. Now, yes, we do have some non-metal solids, but as I go across the table, I go from a solids to gases being on the right side of that table, with, of course, the exception of hydrogen. We've only got 2 liquids. Yes, they're liquids, but there's only 2 of them on the table, so don't stress them because they are color-coded. So my blacks are solids, my reds are gases, my blues are liquids, and my greens are my man-made elements. The other trend that has the same pattern as metallic nature is atomic and ionic radius. And this is if we are comparing atoms that are all neutral or if we're comparing atoms that are all ions. So the reason we actually see the patterns that we see for atomic and ionic radius has to do with one of 2 things. If we're looking at down a group, the pattern that we see is due to the increase in energy levels. So we have an increase in energy levels, therefore my radius is getting larger. So my radius increases as I go down a group due to the increase in the number of energy levels. I know Bohr's model is not the best illustration, but it's the one that I know you've seen and you can draw. So picture adding another ring to your cloud. In reality, the size of our smoke cloud is actually just getting bigger and bigger and bigger every time we go down a group. Now, as we go across a period, my radius has a general pattern of decreasing. It decreases as we go across because of that nuclear charge. It's technically effective nuclear charge. So that nucleus is getting stronger every time I add a proton, and that stronger nucleus is pulling on those negative electrons a little bit tighter. And since it's pulling on the negative electrons a little bit tighter, our cloud is shrinking just a little bit. So my radius decreases as I go across the periodic table due to that effective nuclear charge. And my radius increases as I go down. Really and truly, if you can remember that these three have the same patterns, and I say three because ionic, atomic, and metallic. If you can remember that they have the same pattern, you can infer it from the periodic table, which is kind of nice. So the next set of trends that we're looking at is our ionization, our electronegativity energy. Electronegativity, we see the pattern that we see because of the element's size. Remember that electronegativity is how much I attract electrons. So if we remember that our metals lose electrons and our nonmetals gain electrons, we can easily infer the trend in electronegativity. So if I'm gaining electrons, that means I have a really, really, really high attraction for my electrons, or the electrons of another element. Therefore, I tend to have a high electronegativity. If I'm trying to lose electrons, I have a low electronegativity because I don't want to attract them. I want to give them away. So the pattern we see is that as we go across the periodic table, my electronegativity increases. We get more electronegative because our radius is getting smaller, and smaller elements are easier to attract electrons. But if you think of it in terms of metals giving away electrons and nonmetals gaining electrons, you can get to the same place. As I go down a group, my electronegativity decreases. Larger elements have a harder time to attract electrons simply because there is more energy levels between that nucleus and the outer shell, my valence shell of electrons. So my larger atoms have a harder time attracting electrons. My smaller atoms, it's easier to attract them. Therefore, we see a general decrease in electronegativity. Now, I do want to note with electronegativity that most of the noble gases have no attraction to electrons. Therefore, they have no electronegativity value. And that is kind of important to note when you're trying to figure out who the most electronegative element on the table is. So ionization energy has the same pattern as electronegativity, even though they measure opposite things. Ionization energy is the energy needed to remove an electron. But again, if we think of it in terms of a metal likes to lose, therefore it's going to be really easy to get rid of their electrons. But nonmetals want to gain. That means it's going to be really hard to pull that electron off. We can see a general increase in ionization energy as we go across. And we can see a decrease in ionization energy as we go down. It is easier to steal electrons from our larger elements. It takes less energy to take an electron from the 6th energy level than it does the 2nd. Considerably less energy. Now, I do like to specify ionic versus atomic for the same element. So this is not explicitly a pattern across the entire periodic table. We are looking at comparing individual elements to themselves. So remember that my cat ions have lost electrons. And my cations, when they lose their electrons, they always are smaller than their parent ion. So I'm going to pick on magnesium and magnesium plus 2. Magnesium has lost 2 electrons, therefore its radius is smaller than normal magnesium. If I look at my an ion, my negative ion, we have gained electrons and my radius increases for my ion versus the parent element. So my normal element is going to be smaller than that ion. So let's pick on nitrogen versus nitrogen minus 3. Minus 3 means I've gained 3 electrons. Therefore, my cloud has gotten a little bit bigger because we've shoved 3 more electrons in that outer energy level, and they're going to push away from each other. So we can see that my negative ions are always larger than the parent. My cations are always smaller than their parent. And yes, we can use this to compare ions from our transition metals that have the same element but multiple oxidation states. So I'm going to pick on vanadium plus 2 versus vanadium plus 4. They both lost electrons, but vanadium plus 4 has lost more. Therefore, it's going to be a bit smaller than normal vanadium. And it's even going to be considerably smaller than vanadium plus 2. Here we go. We'll put normal vanadium on the screen. Whew. So my valence electrons, guys, this is that pattern that you should have memorized. So if we count our tall columns, my valence electrons kind of go 1 through 8. So as we go across the periodic table, they increase 1 time, with the exception of my transition metals, but we don't really talk about that exception too much. And my valence electrons, as I go down a group, stay the same. So they remain constant. They don't change. All the elements in the same group have the same number of valence electrons. That's why they have the similar or same chemical properties and similar physical properties, because that outer level of electrons is what determines how that element is going to react. Now, my charge, my ions, ladies and gentlemen, that's that pattern that we need to memorize. If you don't have it memorized, have it on your periodic table so you can look at it. It does not doesn't have a general overall pattern, but I can't think, sorry. We go group 1 plus 1, group 2 plus 2, 13s plus 3, 14, 4 valence electrons. We're halfway there. It could be either or, positive or negative 4. My metals are positive. My non-metals are negative. Now we start to count down. Negative 3 for group 15, negative 2 for group 16, negative 1 for group 17, and 0 for group 18. So I know that this is a lot of information in a little bit amount of space. So instead of it in this format, remember we got our lovely little graphic that has that same information. And I deliberately don't show the inner transition metals on this particular chart or this particular graphic, simply because they really start doing some funky stuff. And we're about the big picture, not about that little picture. So now let's actually use some of our trends to either sequence elements or answer questions. When you're trying to answer trend questions, there's some strategies that will help make it a little bit easier. First and foremost, whether I ask you or not, you really want to write that trend down. Even if it's as simple as just writing the arrow and saying whether it increases or decreases. Having that visual reminder as you are answering questions will help you figure out which element is first, which element is second. Next, you got to find the elements. And that's kind of the challenging part if you've not been playing with the periodic table much. Yes, the trends that we learned for our real table apply to the fictional table. Anything we learn that applies to the real one will apply to our fake one. So you find your elements and you kind of mark them on your table. So if you have a report cover sleeve and dry erase markers, that's great. You can actually use it kind of like a dry erase board. I have mine laminated because I actually use dry erase or ready erase markers on it. when I am doing trends. But if that doesn't work, then pencil and eraser, or Cami and a stylus. Identify your starting point, and then you're going to write your elements in order. So sounds easy, but we've got all those trends. So that's why we start by writing the specific trend that we are looking at. So my first set of questions, we are looking at metallic nature. So remember, metallic nature, as I go across, it decreases because we go from our metals to non-metals. Then I give myself enough room to write. As we go down a group, my metallic nature increases. Because again, we have non-metals on top, metals on bottom. So according to the trends in metallic nature, what is the least metallic element? Well, my least metallic element is going to be an element that's going to be on the right side of the table, because we decrease as we go across. I'm trying to figure out which of my noble gases is the least metallic. Well, if I increase in metallic nature as I go down, that means helium, He, is the least metallic element on the periodic table. The most metallic would be completely opposite of helium, so francium. So for 2, we're trying to put elements in order of increasing metallic nature. Increasing means we're going from smallest or lowest to highest. So make certain you know your terminology. Increasing order means you're starting with the little ones and you're going to the bigger ones. So I've got my pattern on the screen. I increase as I go down. I decrease as I go across. My strategy is to mark the elements on the periodic table. AS, F, FR, HF, and PD. Notice that these kind of sort of form a very loose diagonal. Well, I know helium is the least metallic. That means my smallest in this group is going to be fluorine. And the largest in this group, or the most metallic, is going to be francium. I know the beginning and the end of the sequence. Therefore, I can see that I need to go from top right down to the bottom left. So it would be fluorine, F, AS for arsenic, PB for lead, HF for hafnium, and francium brings up the rear, being the most metallic of that group. So kind of see how that pattern works. I marked my elements, figured out where to start, and then I just listed them based on that pattern. So for question number 3, it is saying decreasing order. That means we're going from high to low, or large to small. But I still want to find those elements. So I've got francium, mercury, iodine, ND, and PB. I really like picking on lead, and xenon, Xe. So be careful with your intertransition metals. You might want to use the extended periodic table if you have an intertransition metal, so that you can actually see that ND, even though it looks like it's at the bottom of the periodic table, element 60 actually really falls right there. So when I'm trying to put them in order, ND isn't going to be at the very end because it's at the bottom. It's actually going to be somewhere in the middle. So decreasing means I'm starting with the largest. Well, my most metallic is going to be francium. So francium would be first. Then we put them in order from how we see them lining up on the table. So ND would come next. travel over on my way to the very edge, I can see that next is HG, followed by PB, followed by I, followed by XE. That's my smallest, francium being the largest or the highest. So it doesn't matter the trend, the process for how you do it stays the same. So this particular group of trends, we are looking at radius and mass just to kind of mix them up. Now, the thing about mass is you definitely want to double, triple check that periodic table because you can read the mass on the table. And there are a few times where the pattern doesn't follow the rules. So my trend for my radius, my atomic or ionic radius as I go across decreases due to that increase in nuclear charge. Stronger nucleus pulls the electrons tighter. And as I go down a group, my radius increases due to adding more energy levels or more shells. So I am going to mark my elements: iodine, indium, molybdenum, lead, strontium, and tellurium. Now notice that all but one of these are in the same period. And that kind of gives me an opportunity to talk about the difference with radius between periods and groups. So it's a very small change as I go down across a group. Very, very small. But as I go down one period, it is a massive increase in that radius. So if I'm looking at radii, or if I'm looking at elements that don't form a nice, pretty diagonal, take it one row at a time. So for my radius, we're doing increasing, which is small to large. So out of all of these elements, iodine is going to be the smallest. And lead, considering it has an additional energy level on top of all the others, is going to be the largest. So if I fill in the things in between, I'm going to go across my fifth period first. So iodine, tellurium, indium, molybdenum, strontium, and then lead brings up the end. Switching colors because I'm switching trends. So my mass, remember I can read that on the table, but in general, we increase across and we always increase down. And the tricky one for my mass in this particular example is that tellurium and that iodine, because that is one of the few times that we have a decrease in mass. So tellurium is actually more massive than iodine, but I can actually see that on the table. So decreasing means we are going from large or largest to smallest. So the largest of all of those masses is lead. And then we can kind of read each of our masses from there. I don't know why I put those so far across. So tellurium is the next largest, with iodine being the next one, followed by indium, followed by molybdenum, and then strontium being the smallest mass. So mass, always double check the periodic table just to make certain it's not one of those weird exceptions. Okay, the example number 3, I'm going to find my elements. I already have the trend written on the table. Radius decreases down and radius decreases across and radius increases down. So AC, really? Okay, I'll come back and find AC in just a second. We got calcium, LR, PA. That's an inner transition metal, so be careful. TE and TH. Wow, I made these really all over the place. And this is why we practice in chemistry, so that we can easily find elements on assessments. Ah, there's AC. Actinium. Actinium. Gotta love it. All right, so I've got circles all over the place. We are trying to go from the smallest to the largest. So the smallest element is going to be the one who's at the top. The largest of the ones are going to be the ones at the bottom. Now notice that I do have 4 that are in the same part or same row of that periodic table. So be careful. So my smallest is definitely calcium because it only has 4 energy levels, followed by tellurium with its 5 energy levels. But now we're going to the next 4, which are all in the same period. So as I go across, we decrease. That means LR is going to be the smallest out of those 4 because it is the furthest to the right. Remember that extended periodic table will help keep you from making little mistakes with putting your inner transition metals in order. From there, I'm just reading the rest of the elements from right to left. PA, TH, AC. So in this particular example, we're comparing elements to ions, to neutral elements or ions, to other ions. Now, that general trend that we saw for ionic radius of increasing down and decreasing across works great if we're comparing 2 different elements. But if we're comparing the same element, comparing that same element, my cations are always smaller than the neutral element. My anions are always larger than that neutral element. So I'm just using 0 to represent any non-ion element. So if I look at Na+1, we have lost an electron, therefore it's smaller. For 2, I've got bromine and calcium, so I can't really look at the charges. That means I'm going to find them on the table. And it'd help if I looked at the real periodic table. Notice that bromine has added that 1 electron. Calcium has lost 2 electrons. If calcium has lost 2 electrons, it has the cloud that has 3 energy levels. And my cloud with 3 energy levels is going to be smaller than a cloud with 4 full energy levels because bromine has went up and gained that electron. So it's kind of a little tricky there. It'd be easy if I were to compare ones in the same group, and I'm going to skip down. Actually, I'm in same charge, so I'm going to skip down and do number 5. Aluminum and sodium, they're both positive. They're both in the same group. So now we're using that general trend. The more positive the charge, the more I lost. Therefore, it's going to be smaller. Aluminum is going to have a smaller radii than sodium. Aluminum's further to the right. So it should have a smaller radius than sodium to begin with. Let's compare aluminum ion to aluminum element. Aluminum ion lost its valence electrons. It was lost an energy level. Therefore, it is significantly smaller. Number 4, sulfur has gained. Sulfur has gained electrons. It has gained electrons. Therefore, it is larger than the neutral atom. Remember, this comparison only works when we're comparing them to the neutral atom. All right, last but definitely not least, group 6, we've got aluminum and we've got phosphorus. They're both ions. So I'm going to look at my periodic table and I'm going to see that they're both in the same family, the same period. But aluminum has lost its valence electrons. It has lost its third shell of electrons, but phosphorus has filled it up. Therefore, phosphorus is going to be larger than the aluminum ion. I would have to say out of all the trends, the ionic radius is the most challenging when you're comparing elements that are across one period, that are across the same period. Once you get beyond the same period, if you're looking at multiple periods across, the increase in energy levels is making a more significant difference in the size of the radius. So the little differences between losing and gaining is not that noticeable. So, if I was comparing, in fact, I'll go ahead and do it. I'm comparing oxygen -2 to calcium +2. So yes, calcium +2 is smaller than its parent ion and oxygen is larger, but calcium lives in the 4th period. So it has 3 energy levels worth of electrons. Oxygen lives in the 2nd period. It has filled it up. It's got 2 energy levels or 2 shells worth of electrons. Well, calcium is definitely significantly larger than oxygen. So that placement on the table for your ionic radius makes a huge difference. Okay, last but definitely not least is our ionization energy. First question, most electronegative element is fluorine, mainly because neon, helium, and argon do not have electronegativity values. Those 3 noble gases have 0 attraction to electrons. So fluorine is the least electronegative, because I don't count the noble gases without charges or without electronegativity values. My least electronegative is going to be francium. Now, with the highest ionization energy, that is helium. Helium is the smallest element on the periodic table, therefore it is the hardest to remove an electron from. It's also already got its full outer energy level, so it really, really doesn't want to lose an electron. My general trend, because Ms. Range skipped that step, for both electronegativity and ionization energy, as we go across, they both increase. As we go down, they both decrease. With the little caveat that electronegativity values for noble gases. So it makes it a little bit tricky. Okay, so I'm just going to do 3 and 4, so I'll show the answer for 5, but 3 and 4. 3, we find our elements. I need to switch colors. Oh, let's hope all of them are on this picture. This picture doesn't include all the elements. Francium, cesium, potassium, lithium, sodium, rubidium. I like problems like these where they form a straight line because it makes it really, really easy, because I just have to look at the trend in that direction. So whether it be a straight line across or a straight line down, these are much easier. Decreasing means we're going from large to small. So decreasing ionization energy means my largest ionization energy is going to be that smallest element. So as I go down, we have that general decrease. So we're basically just going to put these in order from top to bottom. There we go. Lithium being the highest, then sodium, then potassium, then rubidium, then cesium, then francium. So pause the video, you try number 4. See how you do. Aluminum, chlorine, magnesium, sulfur, phosphorus. Again, this one's a nice, easy one because it does form a nice, pretty straight line. As I go across, we increase, and we're putting them in increasing order. So I pick my starting point. Well, in terms of electronegativity, increasing means I'm going from right to left. Magnesium is going to be my smallest, and then I just place them in the order that I see them marked on my table. All right, give 5 a try. I'm running out of colors. I guess I'm going to use green. Silver, iodine, indium, molybdenum, rubidium, and yttrium. So ionization energy, as I go across, increases. And we're putting them in increasing order. So we're going from, we're putting them in decreasing order. Bad Miss Rains. Decreasing order. That means we're going from the largest to the smallest. So my largest ionization energy is going to be my iodine because it really doesn't want to give up electrons. It wants to gain them. The smallest would be rubidium because it really wants to get rid of them. So it's going to be easy to take those electrons, and we can kind of fill in the ones in between in order. So iodine, indium, silver, molybdenum, and then rubidium. So that is it for today. I know it's kind of a long video, but watch it in pieces. Do a few practice problems. I'll say this again in class, but come back, try some more. As always, I am available in the big meet and the breakout meet if you've got questions or concerns about trends or even electron configuration from earlier in this unit, or really anything, pardon me, from this unit.